hopefully you've made it to the end of Unit 7. Yes, this unit is actually pretty short, especially compared to Unit 6. There are only 3 lessons in it, but hopefully this lesson will tie all the things together from the previous parts of the unit. So let me introduce to you something called a slope field. And really a slope field is just a graphical representation of a set of slopes obtained from a differential equation. So remember that a differential equation is just one that involves a derivative, and that derivative represents the slopes for a function. Now it should say in lesson not 8.1 but 7.1, so let's make that change. In lesson 7.1 you learned to solve differential equations by separating variables, and even if you cannot separate the variables and integrate, you can still use a differential equation to plot the slopes for a function. So looking at example number 1, I've given you a differential equation here, and I'm going to ask you to actually find the slopes at 4 different particular points. So if the x value is 3 and the y value is 2, what is the differential equation saying, or what is the slope going to be? In this case it's negative x, so that would be negative 3 over 2. Okay, that would be the slope. For part B, yeah, it would be 1 over 3. For part C, negative of negative 2 is positive 2, divided by negative 1. Of course, that's just negative 2. And then for part D, that would be what? Negative 2 over negative 2, that equals to 1. Now, I have this other question here. It says, why can't you find slopes when y equals to 0? Well, what happens when I plug it into my differential equation? I get negative x over 0. Uh-oh, what does that mean? So, you really can't divide by 0, right? And therefore, the slopes are undefined. Okay? So now in example number 2, I'm going to give you the exact same differential equation in example number 1. Yay! And I'm going to ask you to find and plot the slopes given for each remaining marked point, or the dot, in the plane that doesn't have one of these nice little dashes. So each one of these dashes actually represents the slope at that particular point. So for example, from number 1a, the point given is 3, 2. 1, 2, 3, 2. And notice the slope is pretty steep in the negative direction, and that matches up with the slope of negative 3 over 2. Look over here, negative 1, 3. So negative 1, 3. Ah, that's this point, and you see how the slope is positive, but it's pretty flat? That makes sense too. How about negative 2, negative 1? Negative 2, negative 1. Oh, a very steep negative slope because it's negative 2. That makes sense. And then finally, d2, negative 2. Oh, this one's actually not done, so I get to put it in. Ah, so it's a slope of 1. That means I should be drawing a nice 45-degree upward sloping line at the point 2, negative 2. Okay? So your goal is to actually do the rest in this diagram and figure out what the slope will be and just sketch out what those dashed lines would look like. Remembering, of course, that a flat line means the slope equals to 0. A 45-degree upward sloping line is a slope equal to 1. Downward sloping one, of course, is a slope of negative 1. And, of course, if you want an undefined slope, that would be a vertical line, right? Undefined. Alright? So I'm going to ask you now to use this equation. So, for example, if I have a dot like right here, this would be the coordinate negative 3, 3. So this blue dot, I'm going to just go dy dx. And that equals to negative, what? Negative 3 over 3. That would be positive 3 over 3. That gives me 1. Ah, I know this is a 45-degree line slope here. Okay? So can you please go ahead and do that for all of the points, and then come back and double check your answer with mine when you're done. Notice these are all flat here, right? On the y-axis, because the x value equals 0. So the slope here is all flat. Really steep. Kind of therapeutic here, just drawing these little dashed lines. At least I think so. You might think this is just a pain. On an AP exam, I've never seen them asking you to draw like 24 points. Most of the time they only ask you to draw 6 or 7, so don't freak out. I remember thinking, how do I show things along the x-axis? Because, like I said earlier, they are undefined when y equals to 0. So in this case, I'm not going to draw straight lines like this. I guess I could, but really, what I should be doing is, hey, these are open dots because they are undefined, okay? Undefined, undefined, undefined. Okay, so in a slope field, and this is what actually you've done here, this is a slope field, we don't really use these vertical lines to represent an undefined slope. Instead, I'd rather you just, at that point, put an open dot, okay? Because it's really at a point here, and it's undefined. It does not exist. Okay? So like I said to you earlier, example number 2, what we just drew out, is what we call a slope field. Yeah, this thing. And starting at the point 0, 1. So if I start it right here, I'll use yellow right now, okay? You can follow the flow of the slopes to sketch the solution curve containing the point 0, 1. So remember how we looked at differential equations, and if I didn't give you a particular point, you'd have some equation y equals to blah 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 plus c, which gave you a family of curves. Well, now if I'm saying, look, what if I gave you a point? Well, that family of curves is now narrowed to one specific curve, and it's one that follows along this idea of kind of, and I'll use maybe red in this case, going like this, and coming down, right? So I'm following the flow of the slopes. The idea is that your graph should be parallel to the slope lines and be like an average of the slopes whenever it goes between the lines, right? I don't really have actual dashes, but I can find out that, yeah, this is pretty much parallel to it, so I can actually do a rough sketch. Okay? Now, this is a key point here, and I'm going to ask you to highlight this word. Your solution curve must represent a function whose domain is the largest possible open interval containing the point. Notice that I've stopped drawing it here when I reached the x-axis. Notice I did not continue and go like this. Ah! Why not? First of all, that wouldn't be a function, and second of all, it would have past a point where it's undefined. Okay, so there's my answer for this one. What about this next one? It says sketch a solution for the curve passing through -1, 1. So this time I'll use green, and I want like you to try this. -1, 1 is this particular point right here. And so yeah, the idea is to draw it probably something like this. And once again, when I touch the x-axis, I need open dots. Okay, so that's the one in green. And one final one, I'm going to use black. Actually, I use gray. I have gray here. To the point 0, -3. 0, -3 is down here. And so now I'm just going to try to curve, 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 and hopefully you can see that I'm getting something that looks like this. try and draw it a little bit nicer. It should be more curved. Oh, I'm having a hard time drawing this, but you get the idea. Curved. Curved. Alright, the $1,000,000 question for example number 3. What type of graph does this differential equation seem to be producing? Yes, they seem to be producing semicircles. Okay? Semicircles that open up and open down. Once again, please note, the most common student error when we sketch a particular solution is that you extend the graph way too far and create a graph which is not a function. So in this case, it's always important to set appropriate boundaries for my sketch. And once again, y is the x-axis, a boundary for the differential equation that we wrote down in examples 1 and 2. Once again, because, yeah, the derivative, what do we say it was? Yeah, is undefined at, or I should say when y equals to 0. So notice whenever y equals 0, we cannot actually calculate the slope, therefore we call it undefined, and hence a boundary. Okay, alright, you try this one now. Okay, so I'm going to put together all the stuff from the previous units as well. I want you to solve the differential equation. Yes, okay, using, of course, separating variables. And then once you've done that, I want you to find a particular solution for one that goes through the point. And then after that, hopefully we will then make a connection with our next example as to why this all makes sense with the graphical representation of the slope field. Okay. Number 4. You were thinking, I've seen this equation before. Yes, you have, because it's the same as what? Examples 1 and 2. So really, this is connected to the graph that we just did on the previous page. Okay, so keep this in mind. Snap a picture, right? Keep it in your head as we go about solving this differential equation. So once again, we're going to solve by separating the variables. So dy and y are on the left side, and negative x dx is on the right hand side. Beautiful. Next step, we anti-differentiate. Y squared over 2, negative x squared over 2 plus c. If I want to solve for y squared, I'm going to get rid of that 2 first of all. Negative x squared, we can call this c sub 1 if you want. And if you're thinking, I should solve for y, let's go ahead and do that. Y equals to, don't forget the plus and minus of it. So some constant, I'm just going to call it like big C like this. So solving for y yields 2 possible equations, the square root of negative x squared plus c, or y equals to the negative of the square root of negative x squared plus c. Now, just to make a quick note before I finish this part, this lovely equation here, if I were to rewrite it as x squared plus y squared equals to some sort of constant, what type of equation is this? If you said equation of a circle, you are correct. Hence the semicircles on the previous page, because of a boundary that we had at y equals to 0. So once again, looking at this, hey, do the possible solutions verify these results, right? Does it look like we get what we get from the previous page in our slope field diagram? Yeah, I think we do, because we're pretty much saying we've got a whole bunch of circles if it wasn't for that boundary condition, but because we have that boundary condition, we have a whole bunch of semicircles, and that I think makes total sense, because look at what we have here for our equation for y. When I separate it without the plus or minus, we either have the top half, this is the top semicircle, Or we have you got it, the bottom half of the semicircle. So now if I ask you to find the particular solution for the differential equation, that graph that goes through the point 0, 1, we know this is part of the top half of the semicircle, so I'm going to use the equation from the top half, the square root of negative x squared plus c. I'm going to plug it in now, and notice I can solve for c. Oh yeah, c equals to 1, and we have here y equals to the square root of negative x squared plus 1. And that does definitely match up with the equation in red, right? This is a semicircle with radius 1. Alright, and how about the last part here? It says find the particular solution whose graph goes to the point 0, negative 3. You should be able to do this. But before you do this, which equation do I choose? Do I choose the top semicircle or the bottom semicircle? Yes, because it goes to the point 0, negative 3. That must be the bottom of the semicircle. So let's pick that equation now. Let's plug in the values. And then we'll solve for c. We'll find that c actually equals to 9, which is great. Y equals to the negative of negative x squared plus 9. And that would definitely be a circle, or in this case a semicircle, of radius, not 9, right? Square root of 9 is 3. And that totally makes sense. Because I'm looking here, and look at this. 3 units all around. Okay, now, number 5 is all this together with a separate differential equation. So, I'm going to be quiet now. I want you to try to do this, okay, because we've done it before. Now it's your turn to practice with the different equations, okay? As you do each step, though, by yourself, yes, please by yourself, please come back and double check your work before moving on to the next parts, okay? So I'm going to ask you to press pause now. You know the drill. Work on it. Come back. Check your answer. Give yourself a pat on the back if you got it right. If you didn't, fix it up, figure out why you did it wrong, and then we'll move on to number 6 and 7. Alright, press pause. Now this is an interesting slope field because it only depends on the variable y. So if you think about going across in a horizontal line, they will all represent the same slope. So notice in this case, when y equals to 1, yes, they are all going to be 45-degree lines because the slope is 1, right? 1 over 1. Over here, it's going to be 1/2, so a little bit more flat. 1/2, 1/2, 1/2, 1/2, 1/2, 1/2, 1/2. And over here, it's going to be 1/3, so even flatter. Okay. Now what about on the y-axis? Yeah, we got that same problem again. It's going to be undefined. And then now what about the values below the x-axis? Well, in this case here, the y value is always -1, so 1 over -1, that's a negative 45-degree line. This will be what, -1/2, so flatter. And then the third row here, -1/3, even flatter than before. Okay, so there is your slope field. I have completed part A. Now it says graph the particular solutions passing through the points -2, -1, so I'll do that one first. -2, -1, that's this point, so I'm thinking, probably something like this. And then we have one at 2, 2, so 2, 2 is here, probably something like this. And now I'm going to ask you to solve these differential equations. And when I solve the differential equation, you're solving for y, so you're trying to find out the equation of these two graphs that I've sketched in green and red. Just looking at these, I hope you can see that they look like square root functions. So we should be predicting that this gives us a square root function equation. Alright, let's solve dy dx equals to 1 over y. Separate the variables again. Anti-differentiate both sides. Y squared over 2. This is just 1, so the antiderivative of 1 is just 1x plus c. We can solve for y squared by multiplying everything by 2. You can put down 2c or just call it another different constant like c1. And then once again, if I want to solve for y, we're going to have the plus or minus 2x plus c1, or I'm just going to call it big C. Okay? So as an equation, which is a function, we either have the positive portion, or, I should say or, I guess I would say, or, yeah, I guess it is or, the negative of the root. And that makes sense once again by looking at the graph. It's only one portion. Of course, the positive root is above the x-axis. The negative root equation is the one representing the ones below the x-axis. And then finally, write as functions the particular solutions. So once again, let me try and color code this. Negative 2 comma negative 1. I must use the equation with the negative sign. We will go ahead and plug in the numbers. 2 times negative 2 plus c. Negatives cancel out. That's great. I have negative 4 plus c. We'll square both sides. And c equals to 5. So all that work here to say that, yes, y equals to negative square root of 2x plus 5. That is the equation that connects with this graph here. Okay? And that makes total sense. So it looks like my value of the x so-called intercept open dot should be negative 5 over 2. And I've got this nice square root curve. Same thing now for the other point. So just more algebra, and I hope you did this correctly. Okay, lots of 2's here. Going to square both sides, give you 4. And so look at this. I get c equals to 0. And that works out well too for my equation, because look at the one in green. I have made it so that it goes pretty much to the origin. So y equals to the square root of 2x. Yay. Okay? So if you got all those, give yourself a pat on the back. And if you didn't, make the corrections, please. Alright, finally, 2 multiple choice questions that I'd like you to try. Okay? I'm going to give you some time to think about this yourself first, because it's easy if I just give you the answer. But I want you to look at these 2 examples. Example 6 says, which of the differential equations actually match the slope field shown at the right? So out of those 5 choices, which one matches the slope field given? And number 7 says, if I actually gave you that slope field, I'm not saying which differential equation matches, but I'm saying which actual specific solution to the differential equation could match. So what is the particular y equals to equation that matches the graphs? Or sorry, the slope fields. Okay? So once again, I'm going to ask you to press pause, and I want you to try it. And then once you're done with your educated guess, come back and double check. Alright? You know the drill. Press pause. Alright, so let's take a look at example number 6. I hope you've analyzed the slope fields. I hope one of the things you've seen so far is that all the slopes in this slope field are always positive. Slopes always positive. Because that's important. Because I can get rid of one of these equations right away. I know it's not going to be a. Because if I have a negative x value, so let's say x is -1, I should have had a whole row of negative slopes. Not happening. Oh, wait a minute. I get rid of b as well, because if I had a whole row of y values being negative, like this, they all should be downward sloping, but they're not. Okay. Strike them out. How about C here? X minus y. So, can I possibly have it always being positive in this case? Well, if I were to take a point where x is, let's say, 2, and then y is 3, so that's this point 2 comma 3, 2 minus 3 is -1. Oops, that's not positive. Strike that out too. Okay, so we're left with just D and E. Now the question I have for you is, what else do you see? Hopefully that you see each kind of row here, they seem to have the same slopes, right? If I look horizontally, they have the same dashes, which means that they are dependent upon only what variable? What changes as I move up and down? Yeah, it's the y. So the next thing I want you to see is that the slopes depend only on y. And knowing that now, we can definitely eliminate E, and therefore D is the correct answer. Okay. Now we can confirm this too. Look what happens when the slopes are 0, like right here. Okay, so when y equals to 0, if I use D, y prime equals to 1 plus 0 squared, that totally makes sense. They look like 45-degree lines to me. So once again, another way to confirm that D is the correct answer. Okay, you got D? Say bravo. Now, for example 7, it's another slope field graph, but now I'm saying the slope field for a certain differential equation is shown at the right. Okay, but I didn't ask you for the equation of the differential equation. I said, which of the following could be a specific solution to the differential equation? Meaning, I don't want dy dx. No. I want the solution to it, meaning I want y equals to. Okay? And if you think about what we did before when I did a solution, think back to the previous page, a solution was actually one of these curves, like the one I drew out in green or in red. So now really I'm asking you, can you draw one of these curves? And I guess it could be this one, 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 whatever. But draw one of them, and that should give you a particular shape of a type of equation. And the question is, what equation then matches this shape? Well, is it e to the x? No, because e to the x isn't upward sloping. Okay. Well, is it the lawn graphs? Well, I hope you don't think so, because lawn looks like this. So definitely not E. How about negative lawn? Maybe it's negative lawn. Oh yeah, but remember, if it's negative lawn, it looks like this. There's an asymptote at 0. This graph doesn't look like there's an asymptote at 0, so forget that one as well. And so now we're left with these two examples, B and C. If I look at the equation y equals to negative e to the x, e to the x is a graph like this. Negative would be taking a reflection of this graph in the x-axis. That would be like that. That doesn't look like the graph either. And so if you chose B, you are correct. Okay. Now, in lessons 7.3 and 7.1, you should be able now to show graphically a particular solution of a differential equation, and then also confirm that that solution is the correct graph by solving the differential equation. Of course, if it is possible to do so. Alright, so this concludes Unit 7. You've only got one more to go, and the course is complete. So please take some time to practice the concepts from Lesson 7.3, and we'll see you back here for Unit 8.